Lesson 3 is the conservation of momentum. The most important lesson in this unit, because the conservation of momentum will carry through this unit and all through the rest of this physics class. So what is it? Well, first of all, I implore you to go onto YouTube and watch some videos. Just search for conservation of momentum and watch some intro videos. There's tons of good ones on YouTube. What is the conservation of momentum? It essentially means, like the conservation of energy, that however much momentum you start off with, that's how much momentum you end up with. So, for example, let's say you've got a ball, a billiard ball. Billiard ball is um, hits another one. This one is stationary. Right? This one has some momentum. It hits this one, and then this one moves off, and this one stays still. Whatever the mass of velocity of this one was, will give you momentum. This one here, once it moves off, will have the same amount of momentum, right? As long as this one comes to a complete stop. Maybe this one keeps moving, then the combined momentum of this one and this one will then equal what the momentum of this one was at the beginning. So conservation of momentum, however much momentum you start off with, that's how much momentum you end up with. Some terminology you need to go over quickly, and that is isolated systems, closed systems, and open systems. We're essentially dealing with isolated systems in physics 30 in high school physics, where no matter or energy is allowed to leave or enter the system. And then there's some other terminology you need to be aware of. Just a reminder that when you see a prime symbol, this little tick right here, it means after. So P is before, P prime is after. The momentum before equals the momentum after. And in this lesson, we're just dealing with one-dimensional collisions. So like the billiard ball is a one-dimensional collision, as long as they don't go off at angles, right? Or a train, if a train coupling, they're along the same track, that would be considered a one-dimensional collision. It means just it's along the same line in one dimension. And this is not a formula on your formula sheet. Right here, the momentum total before equals the momentum total afterwards. And then you can expand that, and you say the momentum of one object plus the momentum of the other object before the collision equals the momentum of both objects combined, added together after the collision. And then they further expanded that to get this. This is not necessarily a formula you have to memorize, although it is helpful, and it's pretty intuitive. It's not as complicated as it looks. We have two types of collisions here in one dimension, and that's objects. After the collision, the two objects might bounce apart, or they may stick together. For example, if a train, they go along the train track, and this one here is stationary, and then this one hits this one, not a very good train, and then they couple together, and move off as one single unit. So let's look at example 1, which says a blue billiard ball, a 0.15 blue billiard ball, moving at 8 meters per second to the right, hits a similar red ball. Similar, when it says similar, it means it's the same mass. So you got a blue ball moving to the right, hits a red ball, same mass. If the blue ball continues to move at 2.5 meters per second, determine the velocity of the red ball. So this is before the collision. So before the collision, the momentum of the red ball is 0. The momentum of the blue ball is just going to be its mass times the velocity. And then after the collision, they're both moving. So the blue ball is moving in this direction, and the red ball is moving in this direction, and they both have a momentum, and the combined momentum, in other words, if I add these two together, they are going to equal this one here. The momentum before equals the momentum after, the conservation of momentum. And So let's do this one thoroughly. In other words, we'll go the momentum before, and some people use B before and A for after. But we'll just say the momentum total before equals the momentum after total, which would be the momentum of the blue ball plus the momentum of the red ball equals the momentum of the blue ball after plus the momentum of the red ball after. Now, you don't have necessarily have to go through this procedure with all these steps, but I think it's important that we do it once so that you can see how it works. The momentum of the blue ball will be the mass of the blue times the velocity of the blue. Again, this gets a little tedious with all the subscripts, but then you can see where we're going with it. The mass of the red ball times the velocity of the red ball equals the mass of the blue ball times the velocity of the blue ball after plus the mass of the red ball times the velocity of the red ball after. And once you've done that, it's just a matter of plugging in the numbers and taking into account direction. So here we go. 0.15 is the mass of the blue ball times its velocity, 8. Plus, now I'm not even going to put in the mass of the red ball here because I know that the red ball is at rest, and therefore, of course, its momentum is 0. So I'm just going to put 0. If you want, you can put 0.15 times 0, but we know it's 0 anyway. And then the mass of the blue ball after, it's obviously not changing mass, and it is going 2.5 still to the right, so this is still going to be positive, plus the mass of the red ball times VR prime, which is what I'm solving for, the velocity of the red ball. Okay, and then just do the math, solve for VR. You'll notice I didn't, from this step here, I didn't say, okay, this is the variable I'm solving for, something I'm going to manipulate the equation and solve it for VR. Why didn't I do that? Well, because things like this, that becomes 0. So it makes things much simpler. If you plug the numbers in, often things will cancel out or it becomes much simpler. So typically with one-dimensional collisions, I don't solve for the unknown variable. I would just plug the numbers in. You're going to get 0.815, 0.15 times 8. I don't have my calculator here, so you're going to multiply these two numbers together. You're going to multiply these two numbers together. You're going to subtract that from there, and then you're going to divide by the 0.15, and you're going to end up with V R prime equals 5.5 meters per second. And since it's positive, it's to the right. Okay. Now, of course, some of you are going to say, you can look at that and go, what? Why didn't you just go this minus this? And yes, you could have done that. The only reason that you could have done that it works for this problem, is because they are both 0.15 kilograms. And in most of the time, that's not the case. So that's why I went through this whole procedure, even though I could have just subtracted these numbers and got the correct answer. On to example number 2. Number 2 is where objects stick together. And so we have a clay, 2 balls of clay, one blue, and they're different, as you can see in this one, they have different masses, hit each other and stick together. The blue one was moving to the right at 12 meters per second, and the red was moving at 8.1 to the left. Determine their final velocity. So again, we're going to say the momentum before equals the momentum after, or the momentum total equals the momentum total prime, however you want to do it. It's not really terribly important. This one, and again, we'll do all the steps. So we have 2 balls. We have a blue one. So we're going to go mass of the blue times the velocity of the blue plus the mass of the red times the velocity of the red equals the mass of the blue times the velocity of the blue prime plus the mass of the red times the velocity of the red prime. Now, you're going to look at this and you go, oh, there's a problem here. What is the problem? The problem is if I plug in all the numbers, and let's do that right away, actually. Let's plug in the numbers. The mass of the blue is 2.3, and its velocity is, the blue ball was moving to the right at 12 meters per second, 12. The mass of the red, 5.6, and its velocity is 8.1, but it's to the left. So you got to be really careful here. You must put in a negative. If you don't put in a negative to indicate that they're going in opposite directions, one right, one to the left, then you're going to get the wrong answer. Now, at this point, you're going to notice, well, I've got a problem here. I've got the mass of the blue. I've got the mass of the red. But it says determine their final velocity. Well, so I've got, in other words, like two unknown variables. Well, you don't really have two unknown variables because if they're stuck together, then they're obviously moving at the same velocity. So this here and this here are really just v prime. And if they're both just v prime, we can factor that v prime out, and it's just going to become the combined masses of the two objects, which makes total sense. Right? There's one object here. Well, let's do the right colors. One blue moving to the right, one red moving to the left, and then they hit each other, and they combine together. So you got your red and your blue stuck together, and they have one velocity. And it's going to be, since they're stuck together, it's going to be the combined mass. So that is how you're going to solve that one. And sorry, once again, I didn't bring my calculator, so I can't go through the individual steps with you. But if you multiply this, add this, which really means subtracting because that's a negative there, then you're going to add these two masses. That's a 2.3 plus 5.6. And then you're going to divide whatever answer you got over here by this. And you're going to get v prime equals negative 2.2 meters per second. And of course, the negative means, since we designated left as being negative right here, then that means the two balls the two balls of clay are going to be going to the left. So the final answer is 2.2 meters per second to the left. Right? You can't just leave it as a negative, because the negative, unless you put a legend saying that negative equals left and positive equals right. So you must indicate the direction. Okay, and that's it. That's the end of one-dimensional collisions, which start off nice and easy. In the next lesson, we do two-dimensional collisions, which are brutally difficult, but fun. So on to that next.